Okay, so today we'll talk about sets, which are some of the most fundamental objects in mathematics. So what's the definition of a set? A set is just a collection of objects. So a set is a well-defined collection of objects. Okay, so this well-defined part, this is sort of just a technical thing, because if you try to set up mathematics without a little bit of control over what sets are allowed to be, you can run into things called, different kinds of paradoxes, like Russell's paradox. So for example, there's no such thing as the set of all sets, because that's not a set. But that's like a very technical point that you don't need to worry about in this class. But I just wanted to mention it. So a set is just a collection of objects. The things in a set, the objects in a set, those are called the elements of the set. Right, and so one way to understand a set is just to understand what is and is not an element of the set. Okay, so let's start with some examples. Okay, so really just any collection of objects. So I could write down the set ABC. Right? So here, all I've done is I've just told you exactly which objects are in the set by just listing them. So this is a set with 3 elements. And the elements are A, B, and C, whatever those are. Okay, one important thing about sets is that the order that you list the elements of a set doesn't matter. Right? The set is the collection of the objects. So if you change the order, it doesn't change what collection of objects you have. So this is the same set. On the other hand, if I take some other set like A, B, D, this is another set with 3 elements, but it's not the same set as a set containing the 3 elements A, B, C. So this is a different set. Right, and then in mathematics, by convention, again, the set is just a collection of objects. So if you happen to list the same object twice in your set, you don't count it more than once. That's something called a multiset if you count how many times you include the object. So if I write down the set A, B, C, A, here I've listed the object A twice, but as a collection of objects, it's still just the 3 objects A, B, and C. So this is the same set as the set A, B, C. So this is the same set as before. Okay, so I give this example just to deal with some like small technicalities. But note that in general, listing all the elements in a set one by one, you can't always do that. And in fact, you're already used to not doing that, right? So let me give you some other examples. So maybe in calculus, some notation that used was the closed interval 0, 1. This referred to the set of all real numbers between 0 and 1, inclusive. Right? So this is like sort of calculus notation. But again, this is a whole collection of objects, and you know exactly what the elements of this set are. Right? So for example, you know that 1/2 is an element. Right? Maybe pi over 4 is an element of that set. But like, 1.111111 is not an element. Right? So this is an entire collection of objects, but I haven't listed all of the objects. It's just that you know what the set is because in calculus, you used this notation to mean that particular set of elements. Okay, but another way to write this is in so-called set builder notation, which is sort of very standard. So let me write this set in a different way. This closed interval is the set of all, let me write it first and then explain what I mean. It's the set of all real numbers x such that x0 is less than or equal to x is less than or equal to 1. Okay, so this is, here what I'm using is sometimes called set builder notation. Okay, so what does this mean? So we put the braces at the end and at the start, at the beginning. This means that this is gonna be a set, right? So I put the braces, so I'm considering a set. So this is like this set. Okay, and then for set builder notation, you have like a first part, a bar, which means such that, and then a second part. And then you close off the brace, right? So this is the set of all somethings such that something. Okay, so what goes here are the objects in your set. And what goes here is like the conditions for the object to be in your set. This is roughly how set builder notation works. So here, if we break down this notation, it says the set of all x in R. So what I'm saying is that my objects in my set are going to be things that I'll call x. And this means, have we discussed this notation yet? I think not yet, right? So there's a lot to unpack here. So R here is just our notation for the set of all real numbers. So all the numbers on the number line. And this symbol here, let me use a different color. This symbol here, which in LaTeX is \n, that's the symbol that means, this symbol means an element of. So in the set builder notation, I'm saying take all of the x's that are elements of R. In other words, take all of the real numbers x. This bar means such that that real number is between 0 and 1 inclusive. Okay, so your set builder notation is always, you have set braces on the outside. The first part gives you the objects in your set. The second part tells you the conditions for the objects to be members of the set. And we'll get lots and lots of practice seeing set builder notation. So this is just the first time you're seeing it. It's okay to be a little confused. As you see more examples, you'll get more used to it. Okay, some more basic definitions to do with sets. Given a set, the cardinality of a set, or sometimes the size, is just the number of elements in the set. So the number of elements in the set, you call it the cardinality or size of the set. Okay, this could be finite or it could be infinite. Mark, cardinality could be finite. All right, so that first set that we talked about, A, B, C, this has cardinality 3. On the other hand, we know that there are infinitely many real numbers, so, or it could be infinite. So you would say that R has infinite cardinality. So there could be a finite number of elements, in which case you say the number of elements. Otherwise, you say there are infinitely many elements. Speaking of infinite sets and this notation, let me give you some extremely standard notation that basically holds throughout all of mathematics. Okay, so here's the first one. Some examples of infinite sets. So this one is the Blackboard bold N. Okay, and for LaTeX, you get a Blackboard bold letter by doing \math BB. That's for math Blackboard bold and a capital N. And what is the set? This is the set of all natural numbers. So 0, 1, 2, 3, etc. This is the set of natural numbers. Okay, I said this notation was standard throughout mathematics. One thing that is a technical point is that some people include 0 in the natural numbers and some people don't. So your book, I believe, includes 0 in the natural numbers, which is why I am including it here. But the only bit of potential ambiguity is if you use this notation, people will know you're talking about the natural numbers, but they might not know whether you include 0 or not. So if you're writing something to somebody who doesn't know what convention you're using, you should tell them whether you can include 0 as a natural number or not. Okay, the next important set to know is Blackboard bold Z. And maybe not surprisingly, the way to get this symbol is to do \mathbb capital Z. And Z is for the set of all integers. So what are the integers? They're the natural numbers and their negatives. Okay, so these are, of course, really fundamental sets of numbers. These are sort of the first 2 sets of numbers you learn when you're a kid. Okay, another comment is, this is not a live lecture, so you can't ask me. You might ask, why is the Z, why the letter Z? This is from the German word Zahlen, which means number in German. Okay, Q, that's the next one. Again, the LaTeX is just mathbbq. This is the set of all rational numbers. Okay, what is a rational number? A rational number is just a fraction with an integer numerator and an integer denominator, where the denominator is non-zero. Okay, so maybe it's a good time to write Q in terms of set builder notation. So Q is the set of all. What I'll do is I'll say what the objects are. The objects are going to be A over B, so all fractions A divided by B, such that A and B are integers and B is non-zero. And so again, here, what I've done is I've told you the objects in the set, they're fractions A divided by B. What are the conditions on A and B? I mean, A and B both have to be integers and B has to be a non-zero integer. Okay, and then the one that we just introduced is Blackboard bold R, and this is the set of real numbers. Okay, so it turns out that it's actually kind of tricky to find real numbers. You probably don't do it rigorously until sometime in Math 327, or maybe in the 342 or whatever the number is. Yeah, maybe it's a 400 level real analysis course. I'm not sure, but we sort of all know what real numbers are in this class. So I'm not going to rigorously define the real numbers. Okay, and I said that this symbol that we used before, it means is an element of, and that's how you say whether something is an element of a set. So let's use this example to give some more examples of that kind of use of notation. So you would say that 3 is an element of Z. Right? This means that the number 3 is in the set of integers, which is true. Right? You would also say that like 3 over 2 is not in Z. Okay, so if you were to use LaTeX, you get this by doing a not followed by an in. That puts a slash through your element of symbol. Okay, we know some things that are rational numbers. So again, every rational number is just every number that can be expressed by a fraction, right? So 7/11, that's in Q. Also, like 0.5 is in Q, right? Because you can express it as a fraction, even though I haven't expressed it as a fraction. Right, but we know that stuff like, pi is not a rational number. Pi is an irrational number. On the other hand, pi is a real number, right? As is like E is a real number, right? Euler's constant. Okay, so these are like sets that you learn about early on in your life because they're extremely important sets of numbers. And the notation N, Z, Q, and R is standard. Okay, but already we can define sort of more interesting sets of numbers. For example, maybe I want to talk about the odd numbers. Right, so how could I talk about the odd numbers? Here's another example using set builder notation. So we know what the odd natural numbers are. They're 1, 3, 5, 7, 9, 11, etc. Infinitely many of them. And this is one way to write down the set of odd numbers, right? If you're reading this, I think it's not that ambiguous that you're talking about all of the odd numbers. Okay. But anytime you see a dot, 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 you should be a little bit suspicious, because how do you know what the rule is that gives you the next one, right? So a nicer way to write this, maybe in some ways, is the following. So I'm going to take the set of all little n and n, again, so my objects are going to be natural numbers n, subject to the condition that n is odd. Here's another way to write the set of all odd numbers. Okay, or here's another way to do it. So what is an odd number? If you think about it for a second, an odd number is just something that has a remainder of 1 when you divide it by 2. So maybe the best way to define the set of odd numbers, if you don't know what they are, is it's the set of all natural numbers n, such that there exists a natural number m such that n is equal to 2m plus 1. Here's another way to define the odds. The odds are all the things that are 2 times a natural number plus 1. Right, so 1 is 2 times 0 plus 1, 3 is 2 times 1 plus 1, 5 is 2 times 2 plus 1, etc. This exactly characterizes the odd numbers. Okay, but we'll learn more about even and odd numbers later. I just want to sort of get you familiar with the set builder notation. Okay, now why are we talking about set theory at this point in the class? Well, one reason is because I want to be able to talk about statements that contain variables, right? So back to statements. We said even on the first day that 3x equals 2 is a sentence, but not a statement. Three x equals 2 is a statement. It's a sentence, but it's not a statement because you can't tell whether it's true or false. However, it is a complete sentence. And the reason that we couldn't talk about whether it was true or false is because we didn't know what x was. And so in order to talk about what x is, we need to ground the possibilities for x in some sort of set. Okay, so I'll talk more about what I mean after I've made the following definition. So a variable is a symbol representing an unspecified object that can be chosen from a given set U. Okay, so the set U is called the universal set for that variable. It's the universal set. That's the set of objects that can be chosen to substitute for the variable. Right, so it is the set of objects which may be chosen to substitute for the variable. And we sometimes call a specific member of the set a constant. So a constant is a specific member of the set. Okay, so let's talk about it in terms of this sentence, 3x equals 2. So in 3x equals 2, most of us implicitly, I think when we look at this, think of the things that you're allowed to substitute in for x maybe as real numbers. Or maybe I'm thinking, oh, well, here x is going to be some kind of real number. But this is like an implicit assumption. Nobody told us this. Right? So I would say that we might implicitly assume that the universal set for x is R. Because it makes sense to talk about plugging in real numbers into the sentence for x. On the other hand, if you take, I mean, you could take the set of all animals or something, right? But it's clear that that's not the universal set for this variable, because if you plug in elephant into 3x equals 12, 2 for x, it doesn't make it a statement. So we need to learn about quantifiers, which will happen in the next section before we're really able to talk about specifying the universal sets. But in general, the universal set that you're considering for the variable makes a difference, right? This sentence 3x equals 2, the universal set for the variable matters. So even though we all made an implicit assumption, maybe we didn't all make an implicit assumption. For example, here's a statement. There exists an x such that 3x equals 2. Okay, here is a statement, right? This thing is either true or false. But whether the statement is true or false depends on what you allow for the things to substitute for x. Right? Because if your universal set is the set of real numbers, then the statement is true. If the universal set is the set of integers, then the statement is false. Right? So here, if the universal set is R, the statement is true. If the universal set is Z, it's false. So anytime you're talking about a variable, you need to know what the universal set is. Okay, also, I don't want to give the impression that the only sets are sets of numbers. So if the universal set is, or if it's like the set of all animals, then there does not exist an animal such that 3 times the animal equals 2. That is just a nonsensical sentence, right? So this shows us that somehow set theory is lying behind. I mean, set theory is going to have to play an important role in making these kinds of statements, because if we don't know the universal set, we can't even tell if a statement is true or false. So let me give you another example just so that we know that things are not just sets of numbers. If I write down this sentence, X is French, then even in real life, if I say, oh, that is French, or I should specify whether I mean the universal set is, I don't know, all people, or all Europeans, or all composers, or all culinary dishes, in order for you to be able to make sense of the sentence, right? It's just in normal language, oftentimes. I mean, maybe you don't use sentences like X is French in normal language, but there's sometimes a lot of context which tells you what the universal set is, right? So if I said, oh, that's French, if we happen to be talking about cuisine from all over the world, you sort of know that what I'm talking about is French dishes. Right? Okay. So we'll talk a little bit more about that in 2.4. For now, let's try to get our hands dirty with the basics of sets. Here's our next definition. So we say that A is a subset of B if what? Okay, so to say that if I tell you A is a subset of B, what does that mean to you? Or what should this definition be? Well, it means that every object of A is also in B, right? Somehow B contains A. So if I were to draw a picture of it, to say that A is a subset of B is like B is some big set, and everything in A also happens to be inside of B. That's the definition. So if whenever X is in A, we must have X is in B. Another way to say this is that every element of A has to be an element of B, which is exactly what's represented by this picture. Okay, we use the notation A is a subset of B. Okay, so in LaTeX, this is \subset EQ. This is the notation for this class. Some people don't put the bar underneath it to mean subset. But that notation is actually a little bit ambiguous, whether or not you want to exclude the possibility that A and B are the same set. So for us, we're going to stick with a consistent notation, which is also what agrees with your book. But maybe that's worth a remark. Remark that A is always a subset of itself because it satisfies the definition. Because this means if X is in A, then X is in A, which is definitely true. So it's true that A is a subset of A. It just happens to be the entire set. And so another e.g., the set 1, 2, 3 is a subset of the set 1, 2, 3. Okay, that's the notion of a subset. We say that two sets, A and B, are equal if they have exactly the same elements. In other words, every element of A is an element of B, and vice versa. Every element of B is an element of A. So based on how I phrase the second part of the definition, right, two sets are equal if every element of A is an element of B and every element of B is an element of A. That's the same thing as saying that A is a subset of B and B is a subset of A. So equivalently, A equals B means A is a subset of B and B is a subset of A. And in fact, this is almost always how you prove that two sets are equal. In this class and in your future math classes, you'll often be asked to show this set is equal to this set. The standard technique is to say, okay, well, I'll show that the left-hand side is a subset of the right-hand side, and I'll show that the right-hand side is a subset of the left-hand side. Okay. Now, if you want to specify that A is properly contained in B, what does that mean? If you want to specify that A is a subset of B, but it's not equal to B, which means that it's like actually smaller. So A is a subset of B and A is not equal to B. That's a proper containment. We use the notation A. So in LaTeX, this is subset NEQ. So this is like saying you are a subset, but you're not equal. And say A is a proper subset of B. So this is like if you want to specify that you have a subset, but it's definitely not the entire thing. Okay, so that's subset equality proper subset. We're going to move right along with our basic set theory. Here's one of the most important sets in life, the empty set. So the empty set, the notation is backslash, this notation for empty set. So if you're late taking a look at home, this is backslash empty set. Note that this is different than the Greek letter phi. Okay, people often use, when you write it in handwriting, it might look exactly like your Greek letter phi, but it's not the same thing as the Greek letter phi. Also, I would say that it's a good idea to not put slashes through your zeros, which some people do, because you don't want to confuse 0 with the empty set. But the empty set is just the set which contains no elements. There's one empty set, it's just the set with no elements in it. Okay, so sort of the simplest set that you can possibly have. Let me ask you an interesting question about the simplest set you can possibly have, which is the empty set a subset of 1, 2, 3? Okay. How do we, I would say that it's maybe not that clear what the answer to this should be, because the empty set has no elements in it. We need to go back to our definition of subset. What is our definition of subset? We need to check if X is in A, does that imply that X is in B? So is it true if X is in the empty set, then X is in 1, 2, 3? Is this sentence true? Well, the hypothesis of the conditional never happens, right? So this never happens. No matter what your universal set is, the empty set contains no elements, so therefore there's no X's that are in the empty set. So this part never happens, which means that this is always false. And if the hypothesis is false, it means that the conditional is true. So this whole statement is true. In other words, the empty set is a subset of every set. So for any set A, the empty set is a subset of A because it satisfies the definition of being a subset. Okay. The next thing I want to talk about is a big warning. And the warning is the difference between two symbols we learned today, which is this symbol and this symbol. Okay, this symbol means is an element of. This symbol means is a subset of. So if you write something like little a is an A, well, this means that A is an object that's contained in the set A. Little a is one of the members of A. This notation means that B is a set, and every element that's in B is also in A. Okay, so let me give you some examples and maybe an interesting question for you to work on. If you just remember that the element symbol means is an element of the set, and the subset symbol means is a subset of the set, and think carefully about what they mean, you will quickly learn this will be in your bones soon enough. Okay, so it's very good to say, it's very true to say that pi is an element of R, because pi is a number, it's a real number, therefore it's contained inside the set of all real numbers. It would be incorrect to say that pi is a subset of R. This is bad. This is wrong. Why? Because pi is just a single number. It's not a set of numbers. If you had a set of numbers, you could ask, is this set a subset of R? Is every element of this set also an element of R? But here, the left-hand side is not a set. You can't talk about the elements of the left-hand side. Okay, on the other hand, you could say the set containing pi is a subset of R. This would be okay. Now there's a set on the left-hand side, and you can check every element of the set on the left is also an element of the set on the right. Okay, you would not want to say that this is an element of R. This is bad. Why? Because the real numbers, the set of real numbers contains as its elements real numbers. It does not contain as an element the set containing the number pi. Right? So the real numbers contains a bunch of numbers. It doesn't contain any sets with a single number in it. Also, some other true things is like the set containing pi is not equal to, it's not an element of the set containing R. Okay, so let's think about this for a second. It seems like, well, let me give you some faulty logic. Since pi is in R, the set containing pi should be, I mean, let's do it this way so it's clear that it's wrong. This is wrong because it's false. But it seems like if pi is an element of R, then the set containing pi should be an element of the set containing R. But let's break down what this means. Okay, so this right-hand side is a set. What is it a set of, though? It's a set containing a single element. And that single element is the set of all real numbers. So this side, this set contains one element. The set of all real numbers. The set containing just the number pi is not an element of, that's not the one element of the set on the right. So this thing is not an element of that thing. It's also, by the way, it's not a subset either. So I want to make it clear that the deep red X's mean that whatever written down is false. So again, the set on the right contains only a single element. It has one thing in it, the set of real numbers. The set on the left contains one thing element in it. It contains the number pi. So is every element in the left-hand set also in the right-hand set? Okay, well, the only element in the left-hand set is the number pi. Is pi in the right-hand set? No. The right-hand set contains a single element, which is the set of all real numbers. So pi is not in the right-hand side. Pi is in the real numbers, but it's not in the right-hand side of this. Okay, but it would be okay to write something like this. Pi 1/2 e. This is a subset of the real numbers. That's okay, because every element on the left is an element of the right. Okay, so you can see that, I mean, there's like some subtlety here, right? It's not totally non-confusing. You could easily see yourself messing up some of these things, right? On the other hand, it's not, I wouldn't say it's difficult. You need to think carefully about every sentence that you write down. When you write down a sentence, you really need to mean that sentence. Okay, so all of these, like I'd say the first 6, they're all like kind of related, but there's only 2 that are true sentences. It's pi is in R and the set containing pi is a subset of R. The rest are subtly wrong. Of course, in math, if you're subtly wrong, it means you're entirely wrong. Right? Okay, so now I'm going to ask you to, man, if this were like a live action class, I guess I would give you like 10 minutes to work on this. So here's the exercise. Let A be the empty set. Let B be the set containing the empty set. Let C be the set which contains the empty set and the set containing the empty set. And let D be the set 1, 2, 3. Okay, here are 4 very nice sets. And I want you to tell me which are true and which are false of the following list. Here's your list of things. A is an element of B. A is a subset of B. A is an element of C. A is a subset of C. I'm sure you can see where this is going. Whoops, that was bad. B is an element. Sorry, I haven't done A is an element of D yet. A is an element of D. A is a subset of D. B is a sub-element of C. B is a subset of C. B is an element of D. B is a subset of D. C is an element of D. C is a subset of D. Because I want you to think carefully about these and figure out whether these are true or false, and see, like, as you're thinking it through, think, could I explain this to somebody else very clearly as to why this statement is true and why this statement is false? Okay, but since this is the magic of a pre-recorded lecture, I can now talk about whether these are true or false. So the first one, is A an element of B? The answer to this one is yes, this is true. Because B is a set containing a single element, the empty set. But A is the empty set. So A is an element of B. A is actually the only element of B. Right? You could write B instead of like this, you could write it as the set containing A. That's writing down the same thing. Is A a subset of B? This is also true because we prove that the empty set is a subset of every set. So A is also a subset of B, but for a different reason. A is B's only element, but A is a subset of B because A is the empty set, and the empty set is a subset of every set. Okay, what about A is an element of C? Well, C contains 2 elements, the empty set and the set containing the empty set. Another way to write this down is C is the set containing A and B. So is A an element of C? Yes. It's one of C's 2 elements. Is A a subset of C? Yes. The empty set is a subset of every set. Okay, now with D, is A an element of D? No. D contains 3 elements, 1, 2, and 3. None of those elements are the empty set. So A is not an element of D. However, A is a subset of D because the empty set is a subset of every set. Okay, next, is B an element of C? Yes, C contains 2 elements, the empty set and the set containing the empty set. B is the set containing the empty set. B is one of C's 2 elements. Here's a tricky one. Is B a subset of C? The answer to this is yes. What is that question? Is every element of B also an element of C? Well, B contains a single element, the empty set. That single element is also an element of C, which means that every element of B is also an element of C, so this is true. Okay, now, is B an element of D? No. D has 3 elements, and none of them are the set containing the empty set. Is B a subset of D? No. B contains a single element, the empty set. The empty set is not an element of D, so it's not true that every element of B is an element of D. This is false. Okay, and then C is not an element of D, not even close. C is not a subset of D, sort of for similar reasons as we were just discussing. Okay, so I think that's like sort of a fun little subtle exercise. Okay, so in the last little bit of this section, we're going to talk about truth sets of open sentences. Okay, which is the reason we stuck in sets in the midst of talking about sentences. Okay, so truth sets. Okay, so just recall that, let me give you a slightly different sentence. 3x plus 12 is less than 2 is a sentence but not a statement. Because there's a variable in it and we haven't talked about the values. I mean, the truth of statement depends on the value of x. So this is what we'll call an open sentence, which means that it's a sentence, but there's a variable in it. So it's open whether or not it's true or false. It depends on the value of the variable. Okay, so let me define this carefully. So an open sentence is a sentence, I'm going to call the sentence P and say that it might have a bunch of variables in it, x1, x2, x3, however many variables you want, let's say up to xn. So involving variables x1 up through xn with the property that when specific values from the universal set are assigned to the variables, the resulting sentence is a statement. In other words, when you actually plug in things from your universal set for the variables, you get a thing that's either true or false. Sometimes this is called a predicate or a propositional function, but I'll always use the word open sentence in this class. So for example, this one that we just gave, P of x, if we let P of big X be this sentence, 3x plus 2 is 12 is less than 2, then this is a sentence. It involves the variable x. That's why I've put x as the argument to P, right? So P has a single variable x. And then if you plug in specific values, let's say the universal set is the real numbers here. If you plug in specific real numbers for x, the resulting thing is either true or false. So P of x is an open sentence here. Okay, and I'm just going to make this definition. The truth set of an open sentence, let's say in one variable for now, is the subset of the universal set that makes the open sentence a true statement. Okay, so again, when ambiguous, we need to specify what the universal set is. But once you have a universal set, the truth set of a sentence is just all of the things that you can plug in that make the sentence true. So it will be some subset of the universal set. So in our example, so if the universal set is R, say, then what's the truth set? The truth set is all of the real numbers such that 3x plus 12 is less than 2. So the truth set for our open sentence P of x is, maybe I'll write it like this, all of the real numbers between negative infinity and negative 10 over 3. So these are precisely the real numbers that will make the sentence true when you plug them in for x. Okay, of course, if we have different universal sets, it'll change the truth set, which is why it's important to know what the universal set is. So in this case, it'll just be all of the integers that are small enough. Right? So maybe I'll write it like this. So the truth set for P of X is the set of all integers X such that X is less than or equal to -4. Here's a nice way to write it. Because if X is an integer less than equals to -4, then that inequality is true. Otherwise, the inequality is false. Okay, if N is our universal set, then the truth set is the empty set. There are no natural numbers such that 3x plus 12 is less than 2. Okay, let me just say one last comment, which is if U is, say, the set of all people, then actually P of X is not an open sentence, if that's our universal set for X. Because if you plug in a person, you don't get a statement, right? 3 times John plus 12 is less than 2 is not a statement, right? You don't know if that's true or false. It just actually doesn't even make sense. Okay, so the truth set of an open sentence is all the elements. I mean, it's a subset of the universal set making the statement true. And it depends on the universal set, of course. So we're going to talk in more detail in the next section, which is on quantifiers, which is sort of about talking about which things in the universal set you're trying to plug in for variables. It'll become clear in the next section. Okay, so we'll move on to 2.4 next.